Okay, welcome back. So today we're talking about reinforcement learning, the advanced topics. Okay. So as we have seen in the past, in reinforcement learning, the agent interacts with the environment. It does an action and the environment gives it back a reward as well as a new state as prime. And using that, the agent has to learn to maximize its expected rewards based on the observed sample of outcomes. Okay. And in the previous lecture that we saw somewhere over here, that the Q-learning is one of the main algorithms. There are two different models, as we have seen in the past. There's model-based approach, model-free approach. Q-learning is one of the model-free approaches in which we do not try to learn the transition model and the reward function. Rather, we just try to learn the action state values directly. Those are called the QSA values. S is the state, A is the action, and we just try to learn those values directly. And the way the Q-learning works is it initializes every value to 0. In every iteration, when it receives a new reward, it uses the exponential moving average to update its estimate of QSA. And it uses a decreasing learning rate alpha, which decreases in every iteration little by little. And eventually it stops, the loop stops. Okay. So one of the best things about Q-learning is, due to this remarkable result from 1992, that it does converge to an optimal policy. You do have to make the learning rate small enough. It doesn't quite matter how you select actions as long as you explore enough. So one of the things that we did not cover in this particular algorithm is on how do we choose action A. So that's one of the things we want to cover today. So the main idea in this lecture is that we need to explore new actions. At the same time, we need to use our previous learnings. That's called exploitation. So exploit the values that we have already learned about. So the key idea is on how do we quantitatively balance between exploration and exploitation. There are two different approaches. One approach is called random exploration, and the other one is called exploration function. There are many others, but at least two approaches that we will talk about today. And then we'll also talk about how do we actually quantify and compare these approaches. So let's talk about the simple idea here, extremely simple, to say the random exploration. And the random exploration works, it's called the epsilon greedy algorithm. And the way it works is very simple. Every single time, we will flip a coin, and with a very small probability called epsilon, which let's suppose it's 0.05, we will act randomly. And with the 95% probability, we'll act on the current policy that tells us what is the best action, right? So we have the QSA values. So we know which action has the highest QSA value. We will do that action. That's with the 95% or like 1 minus epsilon probability. And with the small probability epsilon, we will simply act randomly. That's it. Really, that's it. That's called the epsilon greedy algorithm. So the idea here is that one of the problem here is that initially we have to explore the space, but after we have already explored it quite a bit, 5% probability of exploring random actions may seem to be too much. Initially, it may seem to be too little. Later on, it may be too much. So one solution is that you can lower epsilon over time. Now, this can sometimes be confusing for some people because we also know that we're also decreasing the learning rate, alpha, as well over time. But just remember, these two are two separate things. Alpha is the learning rate that's used in the exponential moving average. Epsilon is the exploration. Epsilon greedy is the random exploration constant. That's what we're using. So you can decrease epsilon as well. And just remember, it's a separate parameter compared to the alpha here. Another very interesting idea is called the exploration function. Now, if you're totally new to reinforcement learning and random exploration is the way to go for you, this is perfectly fine. Epsilon greedy is a good starting point here. But another key interesting ideas is exploration function. And the key idea about exploration function is that while epsilon is a system-wide constant, exploration function allows you to distinguish for each state So for each state where you have not explored enough, you will be exploring there with a higher probability. You can achieve something similar by keeping an epsilon per state. And the effect is relatively similar, but the way the exploration function is articulated is, we will call this function fun, where u is the value of the value estimate for that particular state, and n is how many visit count we have. So this is what we'll be using. And then using that, we will be determining in which state we have to explore and where we don't. Now, we will still be changing the bonus back to the state, to the unknown states as well, because of course, once we change the q values, it affects the other q values as well, because the q values for one state action pair affects the v values of that state, which affects the q values of the nearing states as well. So that's a key idea of the exploration function. Again, a very, very, very useful approach. Another idea to keep in mind here is this quantifiable concept called regret. And the regret is simply saying that when we try new actions, of course, we'll make certain mistakes. For example, we might have a QSA value of, let's say, 37.5, but we explore and we did an exploration, and at the time we chose a different action, and the return that we got on that was only 20. So that 17.5 points that we lost represents a regret from choosing the exploration at the time. So in other words, regret is a measure of your total mistake cost, the difference between your expected rewards and the actual rewards. So that's a very good concept of regret. Regret can help you quantify these two approaches. And as regret will, if you use the concept of regret, you can find that the exploration function usually have lower regret than epsilon greedy functions. So in other words, they are actually a better mechanism. Now, after doing all of that, after forcing exploration versus exploitation, the problem with reinforcement learning in larger contexts is that many times it is still out of space. It's out of space, it's out of time. And what do we mean by that? What we mean by that is that Q learning just keeps a table of all Q values, Q state action values. But in realistic situations, there are just far too many states. There's just far too many states, and too many states, we can't even visit them all in training, and we cannot hold them in memory. So instead, what we want to do is we want to generalize. We want to learn about some small number of training states from experience, and then we want to generalize this idea. This is a fundamental idea in machine learning. We see it repeatedly. This is not just in RL, but this is a fundamental idea. As an example, if you see this one, let's suppose we know that this is a bad state because we tried this thing and the results were not very good. But we won't be able to see that this state has something similar in nature to this state. This is also not a good state, but if we haven't tried it, we wouldn't be able to see it. In fact, this state, which is very similar, except one dot is missing over here, is quite bad, but we wouldn't know it because there's a different state from that. So in default Q learning, QSA, this state would be different from this state. So your QSA value would simply not carry over to this one, even though from a human perspective, this is crystal clear to us that this is a bad state and this is a bad state. But the question is on how do we transfer that inference rule to the machine? One of the key ideas in this approach is to use a feature-based approach, feature-based representation. So in other words, don't just think about this state, rather think about many different attributes, features that represent that state. So features can, for example, be distance to the closest ghost. Is there a ghost to my left? Is there a ghost to my right? If I go this way, am I in a tunnel? How many ghosts are there right now on the screen? Am I very close to the big dot, etc., etc. Distance to the closest dot, distance to the big dot, which reverses the roles. And once we have that, then we can describe the Q state with these features, and we would say this feature is 1. So this state is 1, 1, 0, 0, 1, 1, 0, 0, 1. And now our state can be represented with those features. And then what we do is we take a Q function And normally we would have written it as QSA by itself, but now we write using some weights of each of those features. Then we could have many features here. So we say Vs is equal to W summation of Wi Fi of that state S. So the advantage is that our experience is now summed up in few numbers. It's not the number of states that matter, rather it's how many attributes you have that matters. But the disadvantage is that our attributes may not be completely defining the state. So sometimes two states might have the same exact attribute signature, but actually are different states. So in chess, for example, two positions might look similar. One might be winning, one might be losing. And that's the disadvantage we have. But still, even considering the disadvantage, the approximate Q-learning is a very good idea. And this is how it works. It uses concept very similar of the regular Q-learning function, but now instead of the Q values, we'll be changing these weight values. So every feature that was set to be activated, now we will change the W to be based on this specific episode here. So we don't really have the Q values because, as you know, Q values are now the summation of the Wi and Fi values. So really what we have is Q is now represented by these NWs. All states are now represented by these NWs. So every time we have a learning episode, we will simply adjust the weights. That's all we really have to adjust now. We're not really keeping the QSA values, rather we're changing the W values. And the intuitive interpretation is that if something bad happens, then we try to generalize to other states as well, where those features are present. As we can see in this specific case here, that here you have a ghost on this side, a ghost on this side, no nearest big dot. Then if that's bad here, then that'll be bad here as well, even though we have never seen the state, or even here, even though we have not seen the state, because those three paths are the same. So eventually, our reinforcement learning will be able to learn that those features are what's determining the state to be bad. Another key idea, one of the last ideas we touch upon today, is called the credit assignment problem. And the problem here comes from sparse rewards. Whether you're considering a game of Pong or a game of chess, many times it can happen that the agent can have many moves. Perhaps it even gets into a position of advantage or disadvantage, but then ends up losing or correspondingly winning the game, so that the results might have been up till a certain point the agent was winning, then it ended up losing. So now, if that's the only time when we give the awards back to the agent, in that case, we might be able to we might mistakenly give the credit or the debit back to all the states that are leading up to it, even though there was only one action that turned out to be not a good move. In chess, what we might call a blunder, but otherwise maybe there was a game was going pretty well. So if that happens, the credit or the debit might actually be applied to the entire set of moves, but really there was only one move where it should have been applied. So this problem by itself is called the credit assignment problem, on how do we give agent the reward at each step rather at the end minute here. And this problem is called reward shaping. This solution is called reward shaping. But the problem with reward shaping also is that if you try to give agent rewards early on, then agent will just maximize those rewards and still end up losing all the games. So we have to be careful with it. But this is a problem, and this is one of the suggested solutions. That's pretty much what we have for today. Reinforcement learning. We continued our lecture from last time, but we have this, the reinforcement learning, model-free, model-based way. We discussed this idea of exploitation versus exploration, trying to see how we can quantify the regret in each case. How can we make the exploration dependent upon each state, as well as go down over time. How we can take features over all the states so that we don't have to learn each state independently, and also what's a credit assignment problem and what we can do to do that. Reward shaping. And that's a recap on the reinforcement learning. So Go ahead, keep learning.